Sorry, for those who've not been to our meetings before, then my name is Simon Cuthbert and I'm the president of the Glasgow Geological Society, at least for the next few weeks. We're very pleased to welcome this evening Professor Stuart Haszeldine from the University of Edinburgh. We have a very topical and important, probably one of the most important subjects for our talk this evening. If we could all stop having wars with each other and actually get on with dealing with it, we might be doing it a lot better than we are. Topical, controversial comment there. But Stuart, interestingly, given the subject of the talk, started off in the University of Edinburgh and then his PhD at Strathclyde University in coal geology. I actually ended up working in the same place as him in the early 80s for the British National Oil Corporation, which became Britoil, or Turmoil as we used to call it. And then he moved back into the university world. His PhD, incidentally, was with our good friend Roger Anderton. But then he says, so the first half of his career was producing fossil carbon out of the North Sea mainly. The second half was developing research to show that CO2 derived from the burning of fossil fuels safely put back in the ground. And I get the impression from the notes here that his maths are almost as bad as mine, or he's possibly a better comedian, because he said that the third half of his career has been to investigate geological storage of hydrogen, another interesting alternative to fossil fuels. And I'm sure he'll tell us about the rest of the details this evening. So please give a warm welcome to Stuart Haszeldine.
Well, thank you very much, Simon, and thank you very much for all coming out to the first event of the new autumn, I suppose. Interesting to see so many different people coming to this sort of talk. It's good. So I'm going to talk for hopefully about 45 minutes or something. So if I'm still going at 55 minutes, then somebody better pull me off. And I'm going to try and talk about climate and carbon. None of this in any great detail. How I think we know that excess emissions of fossil carbon as carbon dioxide are driving global heating, acidification of oceans, hurricanes like hitting Florida again tonight, and all those things. So we've swapped that type of regime for the luxury of having very portable, low cost, easy to access fossil fuel, which has really been the foundation of the British Empire, of course, by mining coal and industrializing, and then the foundation of great wealth for all of us up to the present day. And so where we are is we're in an interesting switchover place where the central part of what was has been a lot of my professional life in oil and gas now is relegated to lots of parked exploration and production rigs near Invergordon. We're seeing industry, which is historical industry and petrochemicals industry in central Scotland ever since the oil shales were first extracted and refined to make all sorts of hydrocarbon products. Now we're seeing the very strong possibility that that will close down now at Grangemouth and either shift into biocarbon or close completely, depending on how competent the government is. So you can make your own assumptions about that. And there's great enthusiasm from many people for using nature-based processes, often involving planting trees or turning farmland over to become more rewilded land as a remedy for the excess carbon that we've already got in the atmosphere. So I'll touch on those 3 points on the way through, but it's not organized in a sequence or anything rational like that. And the question is, of course, in this time of change, it's very easy to think that you want to continue propping up the past. You want to continue with life as it was before. But I think actually it's becoming more and more clear that's completely unsustainable with the use of fossil carbon. And we've really got to look forward and transition and move into some variant of the future as sensibly and as painlessly as we can. And that means things will change, government needs to lead, citizens like us all need to play our part in trying to do that. But before I plunge off into the realms of climate and everything else, I just want to point out that what this is about is carbon dioxide. And carbon dioxide was discovered, first of all, and named in Scotland by Joseph Black. And Joseph Black was half between Glasgow University, where he probably did actually most of the work on discovering carbon dioxide by heating kidney stones and driving off the gas, which he called fixed air. And then, like many people still do, then he transitioned across to Edinburgh, who've then claimed everything he ever did as an Edinburgh invention. So again, that's again an interesting and relevant local connection. If Scotland was responsible for discovery of carbon dioxide, at least partly responsible for the Industrial Revolution, releasing huge quantities of fossil fuel carbon dioxide into the atmosphere, it would be at least neat and poetic in a way to be a significant part of cleaning up that and moving out through that into the new future on the other side. So I want to start off by looking at this graph, and this is what's known by climate scientists as the Keeling curve, named after the Keeling who decided to go up Mauna Loa on Hawaii on the United States Atmospheric Observatory and measure the content of carbon dioxide every day. And he did that from the late 1950s, and other people are still doing that at the present day. So if you like, this is the longest record, direct record of measured record of carbon dioxide that we have in the world. And you can see that what happens here is, get rid of that, is there's a seasonal variation between summer and winter, summer and winter, summer and winter, but there's a relentless and increasing rate of carbon dioxide increase in the atmosphere in parts per million. So I was born at about 312, okay, and you can decide which you were born at, or where your children were born, or your grandchildren were born, and the numbers all get bigger and bigger and bigger. Okay, so this is a relentless rise of carbon dioxide, and of course this also spans the time from when climate change became understood scientifically in modern scientific terms, through to lots of climate international conferences, incessant government meetings and intergovernment panel on climate change meetings. We're probably up to COP, Convention of Parties 26 or 27 or something like that now, and none of that has made any difference at all to the rate of carbon dioxide increase. So all the actions which are talked about, all the renewable energies which are being built, all the political agreements, all the policies have made no difference at all. So we as a group of humans are in rather a lot of trouble if we believe that the climate modelling says that this increase of carbon dioxide will continue to drive and increase the drive of climate change, and very rapid climate change. And we're now seeing climate scientists talk about tipping points where you move over from one state of the earth and that'll flip over into a different state. So I don't want to I don't want to communicate at all that we've nearly won this battle or we're doing well, because we're not. We're just still scraping at the foothills and haven't even really got anywhere serious. So this curve needs to turn over, flatten, and then decrease back down towards the middle 300s. And there's cumulative emissions, blah, you don't need to know that. So here's an image of the world in February, and I'm just using this to show that global heating can produce excess temperatures simultaneously in many parts of places around the world. So it's very easy, of course, to confuse weather and climate, and weather varies from day to day. Climate varies between years and decades and centuries. So what we're seeing here is exceptional temperatures simultaneously around the world on this particular day, and I take that as, again, the continual breaking of records, and graphics like this I take as very strong evidence that the world is, of course, actually heating up really quite fast. It's heating faster and faster all the time, and this rate of heating we can't detect in the geological record ever. So this is the fastest ever rate of heating that we know of in the geological record. There are numerous explanations for that, of course. Some people choose to believe that it's a natural process and it'll go back to normal somehow. Other people believe that it's inextricably linked with sunspots. I believe that it's inextricably linked with the release of greenhouse gases, and that's the premise I'm going to move forward on. So the heating is one adverse effect, and that's why we should pay attention to carbon dioxide, and that's why I've been trying to work on taking carbon dioxide out of the atmosphere for the past few years, and why I've been working mainly on decreasing the amount of carbon dioxide put into the atmosphere. Both of those will be necessary to decrease the rate of emplacement and to try and recover some carbon dioxide from the atmosphere. And the consequences of this are now really apparent and upon us. So here's a graphic of the world as viewed from the north, and you can see that the Arctic Ocean, of course, has no continent, no land underneath it. The Arctic Ocean is covered with sea ice, floating ice. So when that sea ice varies, it doesn't change sea level at all. You've still got floating ice, or you've still got the same water into the ocean. It's not the heat, it's not the ocean level I'm interested in here, it's the reflectivity. So as this ice grows in the winter, it's very white. That reflects heat coming into the earth and reflects that off very efficiently to prevent warming. But as we'll see, as that goes through time from the middle 1980s towards the present day, that ice increases in the winter, decreases in the summer, comes down the east coast of Greenland. There's a cooling effect there which pulls the Gulf Stream or the mid-Atlantic current northwards to make us very warm. And from about the middle 2000s, then we'll see that the seasonal pattern really starts to change quite dramatically. You can see there's getting less and less summer ice in the Arctic Ocean. And any time now, there's again quite a big jump. There's very little summer ice in the Arctic Ocean, and there's less and less summer ice in the Arctic Ocean. And within probably about 5 years, within 5 years, there'll be no summer ice in the Arctic Ocean. And the implication of that's twofold, that if there's no ice in the summer left, there's nothing for the winter ice to nucleate on. So the winter ice will be thinner than it's ever been before and easier to melt. And also, most importantly, the north of the world will be black rather than white. And so it will not be reflecting heat, it'll be absorbing heat. So it's what they call a negative feedback. It's a bad consequence of what's been happening. So it makes the absorption of heat by the ocean greater. So we're going to go through that tipping point. We're going to jump into a different state. And in that different state, you can take your pick of scientific predictions, but one prediction is that pulling the warm mid-Atlantic ocean current northwards to us will not happen, or will die away. And so actually, although the world might heat, Scotland might get colder. No more palm trees on the west coast anymore. But we don't know. But all we know is there's going to be a big consequence, which we can't really predict. So we need to take seriously those type of effects and look at how can we take away the driver for that. Obviously, we can try to stop or reduce burning fossil fuels. And so the UK is doing actually really quite well on that, having created a policy in 1990, reference back to 1990, that we're going to decrease our use of fossil fuel. We're about halfway. We're using about half the amount of fossil fuel now, half the emissions that we were in 1990. So that's better than any other country in the world. No other countries can do that. So that's great for us to do that. We've shown that we can show the world that that happens, but we need to get the rest of the world to adopt what we've done. And one of the things we have to do is decrease CO2 emissions. And as I mentioned briefly before, that's in two ways: decreasing the emissions which we directly emit from burning coal, gas and oil, so capturing that with the carbon capture step, and then storing that CO2 somewhere below ground, as you'll see in a minute, and also trying to extract carbon dioxide from the atmosphere and put that back underground, which is still a very, very nascent, only just starting field of research. So we know that we can store CO2, and we know we can store CO2 in lots of different familiar ways. You can put CO2 into your greenhouse or a big industrial greenhouse and grow your tomatoes twice as fast by doubling the amount of CO2 in the atmosphere of the greenhouse. So that CO2 goes into the tomato. But that's, to me, great for eating tomatoes. It creates business, people absorb CO2, but it doesn't store the CO2 there for any meaningful length of time. That's stored there for hours, weeks or days, hours, weeks or maybe a month. You can have CO2, of course, added into your fizzy drinks, your iron brew or your beer or your lager. Again, that's stored for weeks or months. We can have CO2 in fire extinguishers, pressurized CO2. You're surrounded by pressurized CO2 every time you come into a building like this with fire extinguishers. And that will stay there quite safely and securely, of course. And it's so safe and secure that we'll even choose to spray the CO2 onto a fire if it happens. So it's not poisonous. But that only stores the CO2 for years. There's a lot of enthusiasm for replanting trees, rewilding, and that's actually a really low-cost method of pulling CO2 out of the atmosphere, and that's good, but it only stores the CO2 in those plants for a few decades, maybe 40, 50, 100 years if you've got a broadleaf forest, and that's not nearly long enough. The climate needs the CO2 to be taken out of the climate for thousands of years, probably about 10,000 years. So although that's very popular, it's not got nearly a long enough time span. And we know then on the right, then we can also use geological methods of storage. So here's a well-established geological method which has worked very well. We've got carbon-rich rock, which is almost 100% carbon in many cases, called coal. When I was young, you could get coal delivered. When I was young, a bit older, you could go to the petrol station and buy lots of bags of coal. And nowadays, it's almost at the state you'd be prosecuted for doing that. So that's a change in my lifetime. It's interesting. But the point is that the duration, the timeline of storage is going to be important. And that's why I've ended up as a geologist wondering what I can offer into this endeavour, with the idea that carbon capture works at places we can combust coal at power plants. We've now finished with coal burning in the UK 2 weeks ago. Natural gas helps to make fertilizer, so there's huge carbon emissions from natural gas making fertilizer to grow food. Heavy industry, which might be glass making, paper making, steel making, also always emits CO2 as an inherent part of the process. And cement production, of course, is responsible for about 8 or 9% of global CO2 just on its own. And carbon dioxide emission there is not just from the fossil fuel burning, it's from heating the limestone to drive off the carbon dioxide. So the idea is to capture the carbon dioxide at all these industrial sources, purify that, and then that can be liquefied by pressurizing to 70 atmospheres or greater, and then transported offshore by pipeline or transported by specialized shipping, a bit like liquefied natural gas shipping, cooled and pressurized. And the carbon dioxide then is injected deep underground, 2-3 kilometers underground, into porous and permeable sandstone reservoirs. And this is a very similar process then to the process by which we extracted and discovered and extracted the oil and gas from those very similar oil and gas porous reservoirs. Effectively, we're turning the flow round. Having taken the carbon out of the ground, we're trying to put the carbon back into the ground. And so the carbon placed back into the ground here beneath a layer of impermeable rock, which we'll call the seal, carbon dioxide, liquefied carbon dioxide injected into that porous and permeable sandstone rock. And that's a reservoir rock, pretty much exactly the same as West Glasgow is made out of. Either the red sandstone or the blonde sandstone are rocks with 20 or 30% porosity in them, so a fifth or a third of that rock is holes in space, and the carbon dioxide fills up the holes in the space where the oil or gas used to be, and we can then survey that and detect where that carbon dioxide is residing deep underground, so we know it's safe and secure, we know exactly where it is, and we can watch to see that if it moves, does it behave as we've predicted. So if it's not behaving as predicted, we have perhaps 10, 20 or even 100 years of warning before that comes out onto the surface again. And so we can intervene to look after that and control that. And the important point here in both of these circumstances is that if we put carbon dioxide deep underground, that's a permanent storage. It's going to be storage for geological timescales. And we only need 10,000 years for the climate purposes. For geological purposes, then we can go to many places around the world where carbon dioxide is naturally stored for millions or tens of millions of years. So we know from analogues around the world that this is an extremely safe and secure method, and we're just trying to engineer and reproduce that. So that also that's why I'm attracted to carbon capture and storage as a geological storage, because that's a way of getting around that impermanence I talked about with tomatoes and beer and all the other things. So we have to go for that long time scale one way or another. And so that's proving to be difficult, because there are lots of different ways of doing this to try and catch all the carbon, and it's so difficult that in a very British way we've kept on re-examining the exam question rather than getting on with writing the answer. And so we're still discussing about what should we capture, who's going to pay for which bit, and how are we going to do that, and is that fair, and does my industry get penalised or your industry get penalised? But the basic idea is that we've got to do that for biomass, not just fossil carbon. If we're going to use biomass by growing trees for fuel or by growing trees for making buildings with, we should then not throw that carbon of that wood away. We should burn that and capture the CO2 and put that back underground. We should do the same with methane gas, with coal, with oil, all the carbon from these fossil carbon products, which could of course be 50, 60, 150, 300 million years old, that carbon in the coal, gas and oil. That all of that can be used in our industries, which make electricity, which make chemicals, which make paper, which make plastics. All of that's really useful stuff for us. And at the moment, all of that carbon dioxide goes up into the atmosphere from all of these sources and adds to the carbon dioxide in the atmosphere. And what we need to do is fit the capture equipment, the chemical solvents effectively on that exit end, and capture the carbon dioxide and put that back underground in rocks like this one here. It's a sample of an oil field rock from 3 kilometers down underneath the sea, and you can see that it's got quartz crystals in there, the sand grains of growing new quartz on to glue the rock together, but there's lots of space in between the grains. That's the porosity, and that's where we want to put the carbon dioxide deep underground into those porous rocks, where it will stay for effectively permanent geological storage. And in addition to all of that, which we've barely started on, in addition to all that, we have to invent new industries which recapture the carbon dioxide from the air. So we can do that with biomass by growing trees, I mentioned. That's the bioenergy carbon capture and storage. And we can also people are building machines which will suck carbon dioxide through the machine, big fan sucking carbon dioxide through and passing the carbon dioxide over sodium hydroxide, running water with sodium hydroxide in it to suck the carbon dioxide out of the air. And that carbon dioxide can then be recovered by heating or converting the sodium hydroxide, and we can take that carbon dioxide and put that back underground as well. And of course that needs to be powered by low carbon energy, so you need your solar panels, you need your tidal energy, you need your wind energy onshore and offshore. So we need to do all of these things to put the carbon back underground. So in detail, all that's complicated. In principle, it's a really obvious type of idea. So it's so obvious, it's strange that it's taking us such a long time to get round to it. So let's look at some of the features of perhaps the more geological features of what's involved with that. So here's a cartoon firstly showing us very simply the properties of carbon dioxide. And carbon dioxide is a gas at the surface, so it's got a big volume. It's surrounding us now. We've got this 420 parts per million. We started off in the room. It's probably got up to about 700 parts per million now, because we're all exhaling carbon dioxide and the ventilation's not that great. But to put that underground, we're not going to inject that as a gas underground, because that's too diffuse, takes up too much volume. And so liquefying the carbon dioxide by pressurizing it, as I mentioned, 70 atmospheres of pressure is the standard practice for trying to do this. So it's pressurizing the carbon dioxide just like it is in a fire extinguisher. And you can see that the volume of that carbon dioxide decreases down to a critical depth of about 800 meters down, where the carbon dioxide changes from being a compressed gas into being a fluid, which is effectively a liquid, but a very low viscosity liquid, special state of the gas, which is very, very low viscosity. And then that still continues to be compressed and decrease in volume. But anywhere in this zone beneath a kilometer, is the zone where you'll be trying to store carbon dioxide, and you can see the density plot here is increased. So it ends up being about the same density, strangely enough, as same density as crude oil. So it's less dense than the water, the pore water in the ground. So the carbon dioxide, like crude oil, wants to float up underground. So if we're trying to store it underground, then we have to make sure we're injecting carbon dioxide deep enough, and we have to make sure it's got this seal rock somewhere on the top, or preferably 2 or 3 layers of seal rock, so the carbon dioxide does not leak out upwards again. So let's have a look at some pictures we might be a bit more familiar with. So here is that what I've just described as a cartoon of sand grains here in yellow, like a cartoon thin section cut of sand grains in yellow, the carbon dioxide fluid shown in white, taking up the pore space and pushing away, displacing the blue water, which is the resident fluid in that pore space. And that needs several, there are several layers of containment which can all work to contain carbon dioxide. So it's it is very possible to make this safe and secure underground. The first layer of security is to have a shale, a mud rock on the top, an impermeable layer to stop the carbon dioxide, physically stop the carbon dioxide from moving upwards and floating back towards the surface. So we need that shale top seal. So all we need to do really is explore for a layer of seal rock overlying a porous layer of reservoir rock. So it's exactly the same as looking for oil or gas reservoirs. And if you can find a structure underground, a fault juxtaposition or a folded dome, that again is a great position to inject your carbon dioxide, just like making an artificial oil field. So the first type of trapping, as I mentioned, is the stratigraphic trapping, or the physical trapping. Carbon dioxide contained underneath this impermeable seal layer, injected by the borehole, floats up, forms a plume underground, and is contained beneath that impermeable layer. If the carbon dioxide moves through the pore space, as it does when you're injected it in one place and it's trying to flow upwards and outwards, the carbon dioxide moves through the pores of the rock, and as it moves through the pores, it's not 100% efficient movement. So it leaves behind little tails of bubbles of carbon dioxide left behind, isolated in the rock, in just the same way as when oil moves through a rock, it leaves an oil stain and a small amount of oil behind. So the more carbon dioxide tries to escape, the more the carbon dioxide leaves behind it. So less and less is possible to escape. So that's the second method of containment. And the third method of containment is something we've just finished working on a bit, is dissolving carbon dioxide in the ambient pore water underground. And we know that carbon dioxide dissolves very well underground in water because we buy fizzy water all the time and drink it. So that's fizzy fresh water, but all we're after doing here is dissolving the carbon dioxide in fizzy salty water deep underground, and we know that the carbon dioxide then makes the water more dense, and so that water will sink rather than float. So it's a fail-safe containment method of storing the carbon dioxide by dissolving it. So that sinks, it stays there effectively permanently. Even if you have an earthquake, there's been test sites around the world, particularly in Japan, who have injected hundreds of thousands of tons of carbon dioxide, and that's withstood magnitude 6 earthquakes next door to it within a few kilometers. So again, that's safe and secure method of storing CO2. And lastly, if you wait long enough and we've got enough reactive minerals underground, then the carbon dioxide will react gradually with the minerals and produce small amounts of carbonate mineral to become solid, locking up the carbon as a solid mineral. And that's a very slow process and obviously a very small amount of carbon dioxide. So the most important feature of this is the stratigraphic trapping, and then which acts instantly, has to act immediately, and the solubility trapping, which from the work we've been doing looks as though that happens within 10 or 20 years. It's a very rapid dissolution process while the carbon dioxide is moving through the rock. So when we're looking for storage sites, geological storage sites deep underground, we're looking for very big, thick sandstones which extend for tens of kilometers. So here's an example of an eroded, thick sandstone extending for tens of kilometers. And this is clearly, obviously, in North America, in the United States. We don't have scenery like that in the UK. And this is unroofed. You would never store carbon dioxide in this particular locality, but what I'm using it to show is you've got a normal, well-bedded, uniform sandstone, but it's thick. It may be 100 meters thick, and it may go for 10, 20, 50 or 200 kilometers. You're after very, very big carbon dioxide reservoirs. And for that reason, we don't look for carbon dioxide storage reservoirs onshore in the UK, because our geology is so complicated in the UK, it's very difficult to go further than 10 kilometers without changing the horizon or some faulting or some breach of the reservoir. But offshore, beneath the North Sea, there is plenty of sandstone like this. And so one of the first things we did in starting this was to try and map out where the sandstones are. And we discovered, of course, that we hadn't really thought about that before. People had been mapping rocks onshore and had been mapping oil field rocks, but they hadn't really mapped the rocks in between the oil fields. So for every oil field sandstone, there's a reservoir and a seal, and of course that goes and continues sideways and laterally tens of kilometers until the next oil field in the Middle Jurassic or the Triassic Statfjord or whatever formation you want to be. So we, in about 2006, I think it was, we started off what turned out to be quite a big project, a pilot project between us in the University of Edinburgh. Lots of really great help from the British Geological Survey in Edinburgh, Heriot-Watt University, the Crown Estate, and 2 or 3 other British universities, and of course about 20 or 30 different companies joined the project because they could see back in 2006 that this was going to be inevitable. Even though nothing much politically has happened in between then and now, the companies were looking much further ahead than the government. So here we've got half of the North Sea, and the Norwegian half is pretty similar. And all I'm doing here is pointing out this is now an online map at co2stored.co.uk. You can dial this up and you can examine reservoirs from the Devonian, Carboniferous, Permian, Triassic, Lower, Middle, Upper Jurassic, Lower and Upper Cretaceous, and the various parts of what we might call Tertiary. And so there's lots and lots of layers in this skyscraper building of stratigraphy in the North Sea, and each of those floors in there has lots of different sandstones, but it's basically, we're looking for continuous sandstones overlain by mud rock. And the conclusion of this pilot study, which was the first time anybody had looked all around the UK for these type of rocks, was that in the UK we have about 70 billion tons of carbon dioxide storage available to store 70 billion tons of CO2. So that's a big number, doesn't mean anything to you, except that let's say now, right now this year, we're emitting in the UK about 450 million tons a year of carbon dioxide still, even though we're proceeding down to about half of what we were. So that means that we can have storage for probably about 200 years worth of how we're behaving. So there's plenty of storage for our carbon dioxide from the UK to be liquefied, injected and stored in the North Sea deep underground. In fact, there's so much storage that we can offer that as a service to the rest of Europe, because it turns out that Scotland's got about half of the storage for the UK, or maybe 2/3, and England's got about 1/3. Norway has got about an equal amount to both the Scottish and English part. So Norway's got the other half of the North Sea, and all the rest of Europe has about 10%. Okay, so all of Europe has to decarbonise, as well as Norway and the UK. So what this means is you can look forward to thinking we've actually got a really valuable asset here in our geological pore space and our geological storage. So it's like the reverse asset of having the luck to have all the oil and gas in the first place and be able to extract that and sell that for a lot of money. We've now got the reverse asset where we can say to European countries, we'll take your carbon dioxide, we'll inject that, we'll store that in our pore space, and you'll pay us lots of money. So this is genuinely the possibility of starting a whole new carbon dioxide injection industry, which should be the same size or greater than the present day oil industry is in the North Sea. So it's a very big industry, not the peak oil and gas of when Simon was talking about Brit oil, that was at the peak. The size of it is just now, but it could employ tens of thousands of people for a 200-year period doing climate cleanup. So it has several attractions, I think. So to investigate these storage sites, then we're just using very adapted techniques from same sort of evaluations we'll do with oil and gas fields. So here's Scotland on the left here, Orkney, St Fergus, where a lot of the gas pipes bringing in gas from the UK oil and gas fields and bringing in gas from Norway come in at St Fergus. And offshore of that is a lower Cretaceous sandstone, the Captain sandstone, with a big long faulted axis to it, deep marine turbidite sandstones, very pure quartz, ideal reservoir, has a previous gas reservoir in it called Goldeneye, which has now been evaluated 3 times, once by Scottish Power, once by Shell, and again by Shell, and eventually it will get developed because we go round in these political cycles of stop-start. Anyway, so here's one sandstone, and that's got oil fields in it, functioning oil fields, so we've got to stay away from those because the companies producing the oil have got the rights to produce that, and you don't want to legally interfere with that. So here's potential storage sites in these 2 depleted gas fields, but under the UK legislation, then the government wants a spare storage site in case one of these goes wrong while you're using it, just to make it difficult. And so the next place along geographically is the May sandstone, MEY sandstone. That's covered with a very widespread shale, a mud rock seal. It's a Paleogene sandstone, top of the stratigraphy. So we can see we've got lots of sandstone there, but then to evaluate the seal, then we did a large project, and this is just showing you this as an example. We did a large project together with people from Aberdeen, I think, and Liverpool universities. And we did this by combining all the wireline logs, which have been, because there are literally thousands of boreholes out here, not tens, not hundreds, but there's 10,000 boreholes in the North Sea. And because we're a pretty organised country, we've kept the records of those, which is a very sensible thing to do. So we can now go back to those records and use those not for looking for oil and gas, but for looking for storage of carbon dioxide. So we can look at the porosity and the wireline logs, we can look at the amount of shale or mud rock in there, we can look at the percentage of that, we can look at the velocity of cementation, look at the porosity, see where the oil was in green here on the porous and permeable parts, and work out then that this must be quite a good seal up here, and evaluate the sandstone and its storage possibilities in that way. So we can start off, here's the Captain sandstone again, St Fergus, and these are pipelines which have brought gas and oil to the land, and where those pipelines go, we can reuse those pipelines to take the carbon dioxide offshore. So if we've looked at this May area here as a regional backup site, we can look at the actual rocks here. Here's one of the shales. There are several layers of mud rocks in there. We can see that the Rugby shale is quite really a bit more silty than you'd like. It's been oxic, it's been bioturbated, just the same way as you do sedimentology on an oil and gas rock to try and understand its physical properties from its depositional environment. Whereas if we go for this Lister shale, then this is much darker, finely laminated, anoxic, very little bioturbation, much better seal rock, much better at containing. So this is the rock we need to look for. And so out of all these areas, oil fields, boreholes, choosing single boreholes to represent a whole area, going right to the North Sea midline, which out of that area, where do you define your backup storage site? And after 2 or 3 years of work, then this is where we define the storage site to be. This is, again, that pipeline going offshore here. So we've defined our storage site to be well served by the pipeline going to the centre of that, and here is the optimal place. So that's an example of how we're using oil and gas types of geology, oil and gas types of evaluation, adapting that into a different purpose for looking where to dispose and permanently store CO2. Again, why don't we look at that onshore? Because it's not big enough. So here's the places, here's the mapping we did showing you the size of stores in proportion to the size of circles. Here are the sites of carbon dioxide emissions onshore. Here are these solid dots, again shown by size of circles, and this was done probably about 2015 or 16, and you can still see we had quite a lot of coal-fueled power stations at that time, and now we have none. So this again illustrates how fast things are changing to reduce our emissions. But let's have a look here, just to give you some idea of why we can't look for storage onshore very easily. Here at the edge of the Viking Graben, the faulted edge of the Viking Graben, deep beneath the North Sea, a Jurassic Age fault throwing down to the east. And here's that magnified here. Here's the edge of the Viking Graben, down thrown to the east. And in the middle of that down throw is the Miller oil field. And I'll zoom across to here. Here's the fault. Here's the Miller oil field. And you can see it's got a slightly unusual shape to it. And that actually turned out we'd been working on the Miller oil field, looking at the cementation of the geology of that. And I hadn't realized for the previous 5 years that this was one of the carbon dioxide hotspots in the North Sea. So it just shows how blinkered you can be. So this is also very rich in carbon dioxide. So it's a great store, because we know it's been storing carbon dioxide for 60 million years in this case. Anyway, so here's the Miller field, a characteristic reuse of an oil field. You could pump CO2 into that, store many tens of millions of tons into that oil field. How big is it? Well, here's Edinburgh on the right. I realise this may be a bit alien territory, but that's the sea to the north, and this is Arthur's Seat here, and I get paid from here somewhere. But if we superimpose the Miller oil field on the Edinburgh, you can get a better idea of how big these oil field structures are, and how you need to have a large amount of space to be able to develop a size of an oil field like that. And then, just like oil and gas, the challenge in evaluating an oil field structure for storage is that you might look at 6 boreholes in there. Okay, so you've got 6 boreholes to understand Edinburgh. So it's like having 6 lampposts of rock. Okay, and you've got to understand Edinburgh from those 6 lampposts of rock, which is what oil and gas people have done all the time in many ways. Okay, to extrapolate from mapping that out, understanding the sedimentology, looking at the seismic reflection data, mapping that geology out in 3 dimensions. So that's what's been done, and that's what's still being done. That's now what's accelerating. Legally, at the time, we were part of Europe politically. Well, obviously still part of Europe geographically and geologically, and we've inherited from that the legal definition of what storage looks like. So here's a cross-section. This is just a cartoon cross-section of the underground, and I'm showing you this for a reason which will become apparent in a minute. And here's a layer of porous rock in yellow, overlain by the cap rock, the seal. And so what we can do is inject carbon dioxide into that porous rock, and the CO2 plume is less dense than the water, remember, so the green CO2 plume rises up and is trapped physically underneath that cap rock, that first type of trapping. As it moves, it's leaving behind the residual saturation, the second type of trapping, and as it accesses more and more water, it's dissolving CO2 in the water, which is the third type of trapping. So this conceptually represents exactly what we're interested to understand. But legally, there's no point in telling a lawyer all that. A lawyer needs something which they can draw on a piece of paper, like making a map of your house or your land or whatever it is that you're trying to buy and sell. Which particular piece of rock do you want the government to license to you? And the answer to that is that it's now legally defined to be in 2 layers, if you like. First of all, the storage unit, the main reservoir, is where you're supposed to be injecting your CO2, and that should stay there. So you don't want a migration pathway out of that. So that's the first and main site you're injecting into, the storage unit. But you also define a larger storage complex, a piece of, and it's up to you as the license applicant applying for this license to use the underground to define the size of that storage complex. And the storage complex is important, so you could have not just 1, but you could have 2 or 3 layers of different seal in that storage complex. Because legally, if the CO2 moves from the primary reservoir, that's unhelpful, and you'll probably be asked to monitor this more closely, but it's not a fail. And if there's other cap rock layers there and the CO2 is caught underneath those, or the CO2 dissolves in the pore water on the way towards the surface, that's not a fail. It's only a fail if the carbon dioxide leaves the storage complex. and comes back towards the surface. So this is an important legal definition that you're allowed to have movement within there and still be counted legally as retaining the carbon dioxide. And that's interesting because this permits you to tackle one of the larger problems, which is how do you know that these 10,000 previous boreholes in the North Sea are going to be CO2 tight. So here's a diagram of a borehole, which I was never given when I was a student, but I've got better at it now. So you drill the hole through the layers of rock. Here's a sandstone, here's a mudstone, and you put down the hole, usually a steel casing, which can be anything from 11 inches to something like 4 or 5 inches by the time you get deeper down. And you need to cement that steel casing into the rock. So there's a cement goes all the way around the casing, and that's pumped in. And that's really difficult to do because these holes can cave in. So the hole in the rock can be anything from 15 centimeters up to 30 or 40 centimeters if you've gone through a soft bit of rock. So you need to pump that cement in and make sure that's set and CO2 is gas tight, because this is the easiest place for gas. If you've injected CO2 into the rock formation down here, this boundary between the cement and the rock, and particularly the CO2, the cement in the casing, is the seepage, made easiest leakage path for the carbon dioxide to come back out. When you've abandoned a well, you're supposed to put in cement plugs at strategic places, maybe 2, 3 or 4 cement plugs up the length of that well. I'm telling you all this because it turns out that about 1 in every 10 wells in the North Sea has one or more of these layers of security imperfectly done, because there's no money in abandoning wells. You just want to leave as soon as possible and get somebody to sign it off. So a lot of these have not been done very well, and we don't yet know how bad or good that's going to be, because nobody's done the experiments of injecting a lot of CO2 into an oil field which may have 10, 20 or 30 previous boreholes in it. So that's a theoretical risk, but if that's all within the storage complex, that's fine. You can have some seepage, you can have even what you might call leakage. A few tons of CO2 here or there is something you can get out of. But sometimes this may go wrong, and I say we're just finding out how to do this, and this is something which is happening right now. There's a test site in an industrial alcohol making place at Decatur in Illinois. They've been injecting CO2 down from their fermentation processes. They've been injecting their CO2 into the Cambrian sandstone at 7,000 feet down, and they've now recently found in March this year that they found the CO2 at 5,000 feet rather than at 7,000 feet where it was put. So that's not where it's supposed to be. That's leaked, and that's actually leaked out of the storage complex in this particular case. So they should have drawn their storage complex to include these other 2 layers of mud rock higher up. So that's now and the CO2's leaked into these 2 monitoring boreholes. But this, in a way, shows that the monitoring's working. It's effective. It's detected a CO2 migration. The CO2's here. It's still several thousand, effectively a vertical mile away from the drinking water aquifer, which is in the top 200 feet. Okay, so still multiple layers of security, but they've breached the legal boundary. So this is now closed temporarily while they work out what went wrong. But obviously what went wrong, the initial reports are that there are holes, corrosion holes in the piping, in the casing which has gone down the hole. So they have put the casing in, they've not used a corrosion resistant casing metal, so they've used the wrong metal alloy for those pipes, and they've also not cemented those in properly, so the CO2's got round the edge of the cement. So, this is a problem, but it also shows that the subsurface industry and the monitoring can handle that problem in just the same way as most oil fields are not routine, produce your oil, walk away and leave it. They need continually looking after, a bit like having, I'll make the analogy of a bit like having a Volvo with lots and lots of safety equipment. You've still got to be able to drive it. Okay, and it's the driving it and how you run it is just as important as all the safety equipment you've put on the borehole. So that's an example of leakage happening, some sort of leakage happening now. Another effect underground is the pressure. As you put carbon dioxide into the rock volume, into the pore space volume, you're putting a greater volume in there than you started off with. So unlike oil and gas, where you're taking volume out and reducing the pressure, as you put more and more carbon dioxide in, it's rather like pumping air into an inner tube. Put more and more air in, the inner tube inflates and increases in pressure. And that pressure can diffuse, will diffuse, and does diffuse sideways, much greater distances than the physical carbon dioxide. The physical carbon dioxide can stay within the sandstone, but the pressure wave from that extends tens of kilometers away from that. And to show you that, a type of example, hopefully this might mean something. This is a map of part of Alberta in Canada, on the big prairies of Alberta. Down here is an oil refinery run by Shell, Scotford Oil Refinery. They produce hydrogen there, and as they produce hydrogen, they need to throw away carbon dioxide. So they built a pipeline, and the pipeline goes to three injector boreholes. That's a 20-kilometer scale bar there. So no problem with that, standard piece of engineering. But what Shell have calculated is that as they pump the carbon dioxide into these boreholes, which is only at 1 or 2 million tons a year, then the pressure wave will extend out as far as the red box. So the direct effects of migrating CO2 might be in the purple box, but the far field effects, the pressure effects, will be in the red box. So you can see that's tens of kilometers across. That's how far the pressure wave will go. And that's a well-known piece of information, type of information. So if we go now to the North Sea, here's the UK, and offshore of the southeast of the North Sea is the Triassic Bunter sandstone. So it's the red bed sandstones around Nottingham or the west coast of Cumbria, which you might have been familiar with. And so here's a map of that Bunter sandstone, and British Geological Survey have worked on this for like 20 years now, because that's where Keyworth is, where their office is, so it's really handy. And here's the offshore part, and here's the offshore part again. Here's the coastline, whatever this is, Hull somewhere probably here. So they're both the same images of the same place. And what the Geological Survey have done in these two examples is they've modelled and simulated that sandstone with, and you can see it's folded, it's got structures on it, and the black dots are where we'd inject CO2 to store the CO2. And they've simulated what if we inject lots and lots of CO2, 20, 30, 40 million tons a year, and the faults are sealing. Okay, they do not transmit fluid flow. If the faults are sealing, then the pressure builds up in these isolated fault blocks quite well. That's predictable. But you still need to understand the connection between this pressure and this pressure and this pressure and this pressure, because you can see this is one of these areas here is about the same as these red areas, this red area in Alberta. So it's the same sort of size scale. So we can predict that pressure will be a problem. Having the faults or the salt walls as impermeable layers between these very large regional areas is an advantage, because it isolates the pressure into that block and into that block. So if you're working in this block, you don't need to talk to the people working in that one. If you're working in this block, you don't need to talk to the people working in that one. By contrast, if these faults are permeable to pressure, which is the simulation on the left, then the pressure communicates and moves across the whole area, so that if you're in this injecting CO2 here, then you may well be affecting what's happening over here. Okay, so it's a much bigger design and planning permission problem, that if you've built your house over here and some neighbours move in and start having all-night bonfires and everything, it affects your house. Okay, so it's a little bit like, what are your neighbours doing is important. So the pressure is, again, a work in progress. It's clear that's going to be important to understand. It's clear that the government as regulator need to regulate that. And that's important because here is the position now in the UK of licensing CO2 storage. So this is an active industry starting to happen now. So the yellow blocks are the oil and gas licenses, where oil and gas has been extracted in the past, The purple blocks are areas which oil companies and developers have requested they get licenses for. So the UK has now issued, I think, 20 CO2 licenses to 12 different companies. Of course, that's nothing in comparison to continuing oil and gas, but the continuing oil and gas development will be greatly decreased now by the political change to the Labour Party. But the point is that here down in the south, those blocks for licensing for CO2 injection are all close to each other. So the question about if you're here and your neighbours are here, is there going to be communication between those two? That's going to be a really important commercial question, which suddenly the industry has realised that that's pressure interference will be something they need to know about. And here are the sites of CO2 arising, the clusters which are now being developed onshore. So these are the two, Teesside and Merseyside, I'll come to again in a few slides' time. These are going offshore to the Triassic Bunter sandstone in this part of the North Sea here, and Merseyside will be going off to the Bunter sandstone here offshore in the Irish Sea. So this is a current research problem and trying to understand it. And the last type of research problem which is really a geographical problem, is that the North Sea turns out to be really, really busy. You know, you look at the North Sea and you think that's wide open virgin space on the North Sea, but if you're in the Crown Estate responsible for licensing the North Sea, this is the sort of map which you have to deal with. So here are existing gas fields, here's Bridlington, here's Hull down here. Existing gas fields, some of these are target structures for redeveloping as CO2 fields. Here's existing pipelines going onshore or bringing stuff to onshore here. Here are fault zones which are not licensed. And here are some licenses for CO2 storage deep underground at Endurance here, and a further one in light blue off here. Same in the Irish Sea, licenses for CO2 storage in that complex of fields here. But then that's fine. The Crown Estate has licensed that for CO2 storage, but somewhere else in the building, maybe 2 floors up, a different part of the Crown Estate has also licensed the same part of the North Sea to build windmills on it. Okay, so the windmills on the seabed have got these sticks, poles, and the windmills on the top, and they're in lines and rows. But it turns out that if you want to then shoot your seismic to understand where the fluids are in your oil field, you can't drive your boat between these windmills anymore because the size of the streamers is too big. So the Crown Estate has licensed with one hand some income from windmills and with the other hand potential income from CO2 storage, and they don't join up. So there's another active line of technical discussion plus also legal discussion about if we've got this structure to store CO2, who gets priority? Is that us or is that you, the wind developer? And can we evolve different ways of using geophysics to maybe put in geophysical monitoring equipment around the site and actually use the windmills as the sound source to shoot the seismic by, instead of shooting bangs from air guns and dynamite into the sea to get the sound waves and reflect off for the seismic? Can we use the noise from the windmills going around to provide our sonic source? So if we're lucky, then we'll do an experiment in Fife underneath some windmills there in the next few years. Move into a different section now. I've probably got 10 minutes left or something, whoever's keeping time. So I talked about the duration of storage before, and I just want to mention that again. So here is a small-scale farming landscape. It happens to be in northern France, but it could be in many parts of Europe. And a lot of people want to plant more forest. A lot of people want to plant more hedgerows or want to change the grazing patterns to have mob grazing or not to plough their fields to capture carbon. And I think that's something you need to think very carefully about, because I don't think that's true. So you can do all those modifications and that will improve the wildlife, and that's great, and we should do that, definitely do that, because as the climate changes, as our country here becomes more like the middle of France or the south of France, and the middle of France becomes more desert-like, a bit like Spain, then the way the wildlife moves, we don't know. And which wildlife and tree species survive, we don't know. So all this is good, but it's cheap capture for carbon dioxide, but it's very short duration storage, as I mentioned before. The storage of this carbon in the hedgerows might be tens of years. The storage of carbon in the forest might be several tens of years. We have no long-lived 1,000-year forests in the UK. They're fragments of woodland for 1,000-year-old forests. So we've been spectacularly unsuccessful at maintaining forest landscapes for hundreds and thousands of years. So the proposition now from people trying to sell you carbon storage credits to assuage your guilt by planting some trees, I would like to see the long-term longevity certificate of that. And if you're buying that to store carbon for 10 years or 50 years, then that's absolutely fine, but that'll be suspiciously cheap. Okay, so if you want to buy carbon storage for thousands of years or tens of thousands of years, you're going to have to pay not £5 for a certificate, but you're going to have to pay £100 for a certificate. So if you're buying any carbon storage certificates, they have to be reassuringly expensive, is what I say to that. And an example of that is here's long-term geological storage, which works really well. Okay, so that I'm happy to sell a 60 million year certificate for storage in Upper Cretaceous chalk, because that's locked up that carbon in that carbonate mud for tens of millions of years. And so these carbon sinks, anybody here who's got relatives or perhaps themselves thinking of buying carbon storage certificates or offsets, then you have to work out exactly what you're buying. Are you buying long duration storage or short duration storage? And that's important because I talked about recovering carbon dioxide. And here's a graph to show you what that means. Here's the emissions in billions of tons a year. This is the historical emissions through time, 1980 up to where we are now. And this is what we need to do into the future to decrease our emissions at twice the gradient, twice the rate which they increased at, to get to net zero around 2050. Okay? And net zero is where we're still allowed to have some emissions, but those are offset or balanced by recovery of CO2 from the atmosphere, by negative emissions. So we're at this point just now. We've maybe topped out, and as some of you may have seen in the national news last week, then we may be starting to do carbon dioxide capture and storage in the UK, and we're starting down this gradient. But we're not we don't know how to do any of this recapture from air. These are still experimental university laboratory projects. So almost by definition, they're 10, 20 years away from being commercial in size. And on this graph, these are starting to capture CO2 from the air in 2022. That's 2 or 3 years ago. We haven't got one built and working yet, so we're already 2 years behind. And so if we want those to be operating to capture maybe 100 million tons a year by 2050, then we haven't even started yet. So we're not going to meet that timescale. So this is another problem of timing and of engineering requirement. And we know what we need to do in all this. We need to switch from carbon energy to very low carbon energy. We need to make that more efficient. We need to capture and store CO2, which we're just starting on. And then we need to recapture greenhouse gas recovery to recover CO2 from the air. And if I've got any more, yeah, that's millions of tons a year. And this graph again shows how far off we are. This is the amount of CO2 stored per year just in millions of tons a year, or tens of millions of tons a year, since the 1970s. This blue line's the work we did. This is past history. This is where we're going to by 2020. And then at the moment, we have very little certainty beyond mid-2020s, because all these projects down here accumulating this 40, 50, 80 million tons a year of CO2 capture and storage around the world, they're all grant-funded projects. They're all government paying out money, taxpayers' money, to make the projects work. Whereas to be successful in climate terms, we need to develop lots of projects very rapidly which are commercially viable. So we need to change the way we approach these projects, not by funding them with grants and subsidy, but by putting a price of value on carbon dioxide stored. So that if you're a company, BP, Shell, ENI from Italy, Equinor from Norway. If you can store CO2 reliably for the long term, then you'll be paid for it. And that perception has greatly increased the number of projects in the past 3 years. You can see they're increasing, but still none of them are actually working yet, though several of them are now on the track to being built. And I think I'm probably in the last 2 or 3 slides, but if we look at that type of graph, here's the same graph, this is the line we need to go down. What does that mean going back to the North Sea in the number of boreholes that we need? So we've got projects in the North Sea which have been working with 1 million tonnes a year injection for the past 25 years. If we extrapolate those, then if we want to meet our target of injecting maybe 20 or 30 million tonnes a year by 2030, in 5 or 6 years' time, then we need to be drilling and evaluating about 100 different boreholes just now to have the quality of information we need to evaluate those sites. Even though we've got information from oil and gas, we need to convert that into CO2 quality information. So we need to be drilling 100 boreholes now. We need to be drilling 190 boreholes in 2030. We need to be drilling 500 boreholes a year operating in 2050. So none of that's happening at the moment. So we might be drilling 2 boreholes in the next 5 years maybe. So again, we've licensed the sites, but we haven't got the commercial activity behind it to drive that progress of rate of progress. And that's because the UK is very slow compared to other countries. Here in this line is a typical timeline for developing the Acorn project, this project in Scotland for taking carbon dioxide away and putting it underneath the North Sea. And so you can see from the start of the project in 2022, then it's estimated to be 2030 before the CO2 goes into the ground. So that's 8 or 9 years to design and build and understand that project. That's very slow, even for something which we're trying, and it's slow because the government is paying half the money. So the government's being very careful with our taxpayers' money, but by being very careful, it's being too careful, I argue, because if this is a climate emergency, we actually want to get on with it, and we have to make some omelettes and break some eggs. By contrast, Denmark has taken 1.5 years to have a climate plan involving carbon capture and storage and to putting carbon dioxide in the ground last year. Okay, so this can be done much, much faster if the government or the country is prepared to take some shortcuts and some risks on not evaluating absolutely everything to the nth degree, but paying people to get on with it. You can actually drive this much faster. So my statement there is we should be doing this much faster, and we should also be investigating what happens after subsidy. So at the moment, the subsidy is there because the oil companies who produce the carbon, predominantly, the oil companies sell the carbon to you and me as petrol or diesel, or it gets indirectly sold as electricity or as heat. And they then blame us for the emissions. Now that's fine for an oil company, but I have no way of capturing my carbon dioxide emissions every year. And I don't think any of you do either. So we obviously need to change the system where the consumer as the end point is getting the blame. We need to change that into what's a much more European system of that the producer takes responsibility for the cleanup of the consequences. So the producer of Volkswagen cars, maybe not a good analogy, but the Volkswagen cars can go back to the Volkswagen factory and they'll be disassembled into all their components and all the different bits will be recycled. The oil companies don't do that, have no wish to do that. They don't want to be responsible to add on that bit of business. So we have to make them. And so quite simply, conceptually, and I'm not going to talk about that for very long, we have to effectively change the rules so that if an oil, gas, cement company is taking carbon out of the ground and the carbon goes into the air, they then need to be responsible for putting an equivalent amount of carbon back into the ground, so that the responsibility and the business and the pricing of that stays with the oil company. So we call that the carbon take-back obligation. So it's often talked about in the past 2 or 3 years in academic circles, but it hasn't reached the elevated levels of government yet. So the last 3 slides now, of course, as some of you might have seen, on the 4th of October, Friday, a week or so ago, UK government announced that it's allocating 21 billion to carbon capture and storage. And that's to develop those two clusters of projects, one at Teesside, one at Merseyside, create initially 4,000 jobs and hopefully be matched with billions of pounds of investment from other industries. And that 21 billion is over a 25-year lifespan. So it's only, it sounds, they've deliberately chosen a very big number to attract the interest of industry. So they've priced that for the whole duration of the project. But of course, it's only 800 million pounds a year. Only, you know, it's still a lot of money. But actually, if that's starting to decarbonise half of your industrial system, then that's actually quite cheap compared with having lots of money and a dead planet, or having less money and a thriving planet. Then choice seems obvious to me. So what this is doing is subsidising and co-developing a power plant with carbon capture and storage on the east coast, the biggest gas-fueled power plant with carbon capture and storage in the world, a big hydrogen production plant on Teesside to take methane gas as it comes in from Norway, split the carbon and the hydrogen from methane. The carbon will go into storage, the hydrogen will go through the gas pipes and maybe end up with you and me in our houses as a clean replacement for methane. And then on the west side of the country, decarbonising a cement works, decarbonising a gas and a waste combustion plant for domestic waste, a lime plant, again inland in the Peak District, making cement, and a big lot of hydrogen production. And so now Britain's come from being quite confused about what it was doing in the past 10 years. This is now the world's largest carbon capture and storage offer for industrial development. And hopefully it'll work. And it's milestones on the way. It should work. It's been planned for many, many years to start injecting 2 million tonnes a year in 2028 and have that scaled up to 30 million tonnes a year in 2030, and to get to 100 million tonnes or more by 2050, and to start importing CO2 from Europe and charging money to European countries as well. So this is the start of this new offshore industry that I was talking about. So in terms of cartoons, here's the East Coast project, reindustrialising Middlesbrough and Teesside, sending the carbon dioxide offshore to be injected into one of those bunter sandstone structures offshore. South Humberside and the whole Humberside region also doing the same sort of thing, including lots of extra power stations and methane gas storage, sending the spare carbon dioxide off to a different part of the same structure. And in Merseyside, a big emphasis on hydrogen production, reusing the old oil refinery here, which was a big Shell oil refinery, now completely defunct, to turn methane gas into hydrogen, take the carbon dioxide offshore in the orange pipes, and to store that in a depleted gas field offshore. And then sell that hydrogen to all these other businesses in the black pipes to decarbonise, to switch the fuels from methane gas or from oil to zero carbon hydrogen. And then on the following Monday, on the 7th of October, don't bother reading all this if you don't want to, Ed Miliband stood up again in Parliament in London and basically said, we are going to develop the Scottish projects as well, the Acorn project, which we've been had parked in Scotland since about 2010 or 2011. And it's always just slipped down behind all the English projects, even though it was ready to go in 2010. But now this looks like an official commitment, but of course that's just words, but it's more words than you ever had previously. And this is what the Acorn project would look like: to take CO2 from the Central Belt, from Grangemouth industrial CO2, from fermentation plants here, to use an old previous oil and gas pipeline, instead of bringing oil down from the North Sea, to take the carbon dioxide up to St Fergus and then take that offshore to where I showed you with the GoldenEye project in that fault-bounded lower Cretaceous sandstone, and then if necessary to that May storage site further offshore. And that's why I talked about those earlier on. And the types of numbers involved are, we could install sucking carbon dioxide out of the atmosphere, 10 million tonnes a year from that. We think we can probably get 2 million tonnes a year of fermentation CO2 quite easily. Where's that from? That's from Tennant's beer making and big industrial distilleries, as well as the malt distilleries on the north, around the north. 12 million tons of industrial capture if we manage to re-industrialise Grangemouth, and bringing in carbon dioxide from Europe by tankers to Peterhead, shipping tankers to Hound Point here, and using the Cromarty as now as a free port, again as a deep water port, to bring in carbon dioxide to there if we wanted to. So it can completely change the polarity of Scotland being way away on the north to Scotland being a central part of that carbon dioxide disposal system. And the last slide now is, those are all very big projects I've talked about for the past 50 minutes. Very big projects. There's also some small projects, and this is one of them. This used to be called Carbon Capture Scotland till last week, 2 weeks ago, now called the Carbon Removers. What this is a very small startup company employing about 20 or 30 people. Here's an anaerobic digester on a farm, big farm down near Dumfries, and for the past 2 or 3 years this carbon dioxide, this fermentation unit produces methane and carbon dioxide. You can separate those two gases with a membrane, and the methane, biomethane from grass and from cows, goes into the gas grid, and that forms about 5% of our gas supply. And the carbon dioxide by these guys is now being captured with this unit here. That carbon dioxide is being captured from that tank, purified, being turned, at the moment it's been turned into dry ice and sold for transporting vaccinations and pharmaceutical uses. But they're now putting the carbon dioxide into these round tanks which fit on the back of trucks as pressurized liquid carbon dioxide, and those tanks will be going off to Denmark and to Iceland for injecting CO2 underground. And if another one of the projects we've got in discussion with Scottish Government could be working in 6 months, we might be able to store that in Scotland as well. So we'd have our own domestic, self-contained carbon capture and recapture and storage industry. And this one's working. This is at Invergordon Distillery, apparently. I haven't been there yet, but if you want one and you ever go across to the other side, in Gorgie, there is one of these installed at the North British Distillery, so that'll be the next one. So this is happening now. This is not millions of tons a year, this is tens of thousands of tons a year, but this has enough plans to scale up, and the ambition is to be doing at least 1 million tons a year by 2028. And I think there's enough bio CO2 to do 10 million tons a year by 2035. And so that would mean Scotland would be becoming carbon negative by taking the CO2 out of the air. So that's it. So last slide, what I've said is carbon capture and storage is essential. What we've got to do, we've continually failed. We're already 40 or 50 years too late, so another week or two doesn't matter, but the problem is getting worse rather than better. I advocate geological storage because it's large, secure, very monitorable. It's easy to develop. We've got the infrastructure, we've got the expertise, but we're going far too slowly, and we're not charging the money in the right places, and we need to move from subsidy into markets and mandates, forcing oil companies to store their CO2, which is what a couple of legal judgments have said in the past 3 months. And we now are at the point of starting this new industry during the next 25 years. And what we can do with that is we can identify the problem, deploy the remedy, and even make some money out of it at the end of the day. That's it. Thanks very much.